Hi, it's me, Dr. Prasad Putilam. Continuing my classes on superconductivity. This is class number 3. In previous class, I explained about the basics of low temperature conductivity as well as Misner effect. So this particular class, I'll explaining about type 1 and type 2 superconductors, their mechanism of conduction, as well as the comparison between type 1 and type 2. So type 1 and type 2 superconductors, the ratio of London penetration depth, to explain what are type 1 and type 2 superconductors, we need two lengths which are known as London penetration depth as well as the coherence length. Coherence length we call as psi. Okay, which determines the superconductor is type 1 or type 2. London penetration depth lambda, it is a measure of how deep a magnetic field can enter a superconductor and remain at a certain strength compared to the strength at its surface. Okay, if it schematically represent, in case of normal conductors, the field penetrates, whereas in case of superconductors, the field is not penetrating as such, but a little bit penetration may possible inside the surface. So this area in which the magnetic field penetrates to the superconductors, that area or that distance is known as the penetration depth. If you see what is the coherence length is the measure of the distance within which the semiconductor electron concentration. So the electron concentration we represented with this symbol, which cannot change drastically in a spatially varying magnetic field. That means the electron concentration in the semiconductor, to which extent it will not be affected by the external magnetic field, that measure is known as the coherence length. Okay, if you try to understand more about the penetration depth as well as the coherence length, I'll plot a graph with HC. So here it represented the penetration depth, London penetration depth. So on this much distance it will go, the magnetic field go inside the superconductor. Whereas with the coherence length, if I plot along with that, so this is the electron density, it goes to infinity. So this much electron density is not affected by the external magnetic field. So that represents this distance from here to here, it represents the coherence length side. So the ratio of penetration depth, London penetration depth to the coherence length, that value K, the K is known as the constant value known as Ginsburg Landau parameter. Based on that, if the value K is higher than 0 but less than 1 or 1 by square root of 2, then we call it as type 1 superconductors. Okay, or you can say K is less than 1. If K is higher than 1, like greater than 1, or K is greater than 1 by square root 2, we call them as the type 2 superconductor. So the you can see the penetration depth, London penetration depth is higher, whereas the coherence length it is less. Or we can say that in case of type 2 superconductor, the coherence length is smaller than the penetration depth. So if I plot both together, type 1 and type 2, here in the first case, K is less than 1, a second case, K is greater than 1. So this way we can represent type 1 and type 2 behavior. So if you take the examples for penetration depth as well as the coherence length, in case of tin, that is type 1, 3.4 is the lambda, 23 is the psi, it is taken in power of 10 to the power minus 6 centimeter, and the K value lambda by psi, that is 0.16. In case of aluminium, 1.6, 160 and 0.01. Lead, it is 3.7, 8.3 and 0.45. Cadmium 11, 76 and 0.14. Type 2 semiconductor with an element, niobium is an example for elemental type 2 superconductor. Its value, lambda value is 3.9, psi value is 3.8 and the K value is above 1, that is 1.02. Type 1 superconductors, if you discuss in detail, if you plot a graph of magnetization versus applied magnetic field, superconductivity is abruptly destroyed when the strength of the applied magnetic field rises above a critical value. Normally exhibited by pure metals like aluminum, lead and mercury. The alloys which exhibits type 1 superconductivity is tantalum silicide. So not many alloys exhibit type 1 superconductivity. TaSi2 is exhibiting the type 1 superconductivity. Type 2 superconductors, if you plot the graph of magnetization versus applied magnetic field, they do not exhibit complete Meissner effect. Okay, so complete Meissner effect is not exhibited type 2. They exhibit a mixed stage, that is intermediate of between type 1 and type 2 behaviors together present inside. Because it exhibits an intermediate phase of mixed ordinary and superconducting properties at intermediate temperature and fields above the superconducting phases. Okay, it has the type 2 superconductor has two critical magnetic fields Hc1 and Hc2. Below Hc1 it behaves as type 1, and above Hc2 it becomes a normal conductor. It loses its superconductivity. They are usually made up of alloys and complex oxide ceramics, whereas type 1 they are mainly made up of metals. Type 2 they are mainly made up of alloys. Niobium, vanadium, and technetium are example for elemental type 2 superconductor. Boron, doped diamond or silicon are also example for type 2. Metal alloys like niobium, titanium, and niobium tin are also example for type 2. Cuprate, perovskite, ceramic materials which have achieved the highest superconducting critical temperatures. Examples are lanthanum, barium, copper oxide, or bismuth, strontium, calcium, copper oxide, or yttrium, barium, copper oxide. Mechanism of conduction, if you see in check in case of type 1 and type 2, the applied magnetic field or say magnetic flux B and the temperature T are the main two factors controlling the superconductivity behavior. So if you plot B versus T, BC1 is the region, or it can represent, or we say that region A, where both type 1 and type 2 superconductors display the Meissner effect. If you increase the magnetic flux, okay, so the type 1 behavior, that A nature, if you represent with the MH diagram, you can say that both type 1 and type 2 superconductors are following the Meissner effect. If you increase the magnetic flux, we reach to a stage known as B, in which type 1 loses its superconductivity, whereas type 2 it continues. It captures in the magnetic type 2. They capture some of the magnetic field through its vortex or vortices. Only type 2 superconductors within this region having the superconductivity. So if you represent with the MS diagram, you can see on increasing that magnetic flux B, uh, the type 1 superconductors, they reached their maximum possible superconductivity region HC, whereas type 2 it continues, the magnetic field penetrates through the vortices. Okay, further increasing the magnetic flux, more number of vortices are improved. Whereas type 1, it becomes already becoming a normal conducting state, but here type 2, it further continuing to the superconducting state. That is represented by B. C represents the non-superconducting nature. That means above a particular magnetic flux, the material will not show superconductivity. Both type 1 and type 2 will lose its superconductivity. If I represent with MH diagram, we can say that normal conducting stage is reached for type 2 conductor also. In case of type 2, it also features the formation of magnetic field vortices, which I represent, which is represented here. We can call it as a whirlpool or whirlwind, just like whirlpool and whirlwind, but we call it as vortices, magnetic field vortices. So it increases as the magnetic field increased, the number of vortices also increased. It occurs above a certain critical strength of Hc1. After Hc1, the vortices start appearing, and its density increases with increasing field strength. If you compare type 1 and type 2, first comparison, low critical temperature in the range of 0 Kelvin to 10 Kelvin in case of type 1, and high critical temperature greater than 10 Kelvin. Low critical magnetic field typically in the range of 0.000049 Tesla to 1 Tesla. In case of type 2, it is greater than 1 T. Type 1 are perfectly obeying the Meissner effect. Magnetic field cannot penetrate inside the material, whereas type 2, they are partially obeying Meissner effect. Type 1 exhibits single critical magnetic field, we call it as Hc, whereas type 2 shows two, Hc1 and Hc2. Type 1 easily lose the superconducting state by low intensity magnetic field, but type 2 will not lose so easily. Type 1, the transition from a superconducting state to a normal state due to the external magnetic field is sharp and abrupt for type 1 superconductor, represented in the graph, whereas type 2, it is not that much abrupt. Due to the low critical magnetic field, type 1 superconductors cannot be used for manufacturing electromagnets for producing strong magnetic field and have limited technological application, whereas type 2 has got a even wider technological applications. Type 1 superconductors are generally pure metals, and type 2 they are mainly alloys or complex oxides. Type 1 obeys BCS theory. BCS theory can be used to explain the superconductivity of type 1, whereas BCS theory cannot be used to explain superconductivity of type 2 superconductors. Type 1 are completely diamagnetic, but type 2 are not completely diamagnetic. Type 1 are soft superconductors, whereas type 2 we call it as hard superconductors. Type 1 they are called as low temperature superconductors, whereas type 2 is high temperature superconductors. No mixed state exists in type 1 superconductors, whereas mixed state is exists in type 2 superconductor. Slight impurity does not affect the superconductivity of type 1, but even a slight impurity greatly affects the superconductivity of type 2 superconductors. Okay, that's about type 1 and type 2 superconductors. Thank you very much for watching and have a nice day.